So, get this. What if I told you that the difference between a beam of light and the force holding an atom together all comes down to one super simple question? Does the order you do things in actually matter? We're going to dive into this because this one little idea from math, from the language of symmetry, well, it literally writes the rules for our entire physical universe. All right, let's kick things off with that very question. If you do a bunch of things, does changing the order change the final result? I mean, sometimes it does, and sometimes it really, really doesn't. And that simple difference, it has some absolutely massive consequences. Let's see it in action. Okay, I want you to imagine you have a book sitting upright on a table. For our first path, we're going to do two simple rotations. First, let's tip it 90 degrees forward, so it's now lying face down. Easy enough. Then, from there, we'll rotate it 90 degrees to the right. Take a good look at where it ends up, lying flat with its spine facing away from you. You got that? Okay. Now let's hit the reset button. The book is standing upright again. We're going to do the exact same two rotations, we're just going to swap the order. So this time, first we rotate it 90 degrees to the right, and then we rotate it 90 degrees forward. And look at that. The final position is completely different. Now it's lying on its side with its spine pointing down. So here's the takeaway. For rotations in 3D space, order isn't just some tiny detail, it's everything. It totally changes the outcome. Now, this whole idea of order in operations, it's not just a neat party trick with a book. Nope, it's actually the key to understanding symmetry. And for a physicist, symmetry isn't just about making things look pretty, it is the fundamental language they use to write down the laws of nature. And the specific grammar for this language? It's called group theory. It sounds complicated, but really, it's just a formal way to take all the possible symmetry actions you can do, like our rotations, and study them as a complete set, as a group. It's the toolbox for talking about symmetry. And for a set of actions to be part of this group, it just has to follow four pretty simple rules. You can think of it like joining a club. First is closure. If you combine any two moves from the club, you get another move that's already in the club. Second, associativity. How you group the moves doesn't matter. Third, identity. There has to be a do-nothing move. And fourth, inverse. Every single move has an undo button. Okay, so within this language of groups, there are two major dialects. The first one is called Abelian. This is the simple, the predictable, the orderly dialect, where, you guessed it, the order of operations does not matter one bit. The formal rule for this is called the commutative law. It just says that doing action A and then action B is the exact same thing as doing B, then A. The final result is always identical, no surprises. And what's so cool about this is how simple the examples are. I mean, basic addition is Abelian. 2 plus 3 is the same as 3 plus 2, right? It doesn't matter which number you start with. But here's the kicker. This exact same simple, predictable rule also governs the force of electromagnetism, described by a group physicists call U1. But now, let's talk about the other dialect. This is the non-Abelian world, the world of our book puzzle. This is the complex, messy, intertwined world where order is absolutely everything. And the rule here? Well, it's pretty much the exact opposite. In a non-Abelian group, you can find at least one pair of actions where doing A, then B, gives you a totally different result from doing B, then A. The operations, as they say, do not commute. And hey, the examples here should look pretty familiar. 3D rotations, just like we did with the book, they form a non-Abelian group called SO3. But, and this is the huge part, the fundamental forces that live inside the nucleus of an atom, the weak force and the strong force, they're also described by these more complex order matters rules, using groups called SU2 and SU3. So let's just do a quick side-by-side. You've got Abelian groups, commutative, simple, predictable. They describe things like electromagnetism. Then you have non-Abelian groups, non-commutative, complex, intertwined. They describe the nuclear forces. And this isn't just some abstract mathematical detail. This has dramatic, real-world consequences. All right, this is it. This is where it all clicks into place. Let's connect these two mathematical dialects directly to the fundamental forces that literally build our reality. First up, electromagnetism, the force that gives us light, electricity, magnets, the whole show. It's governed by that simple Abelian group we mentioned, U1. Its symmetries are nice and orderly. Order just doesn't matter.
So what's the consequence of that? It's why photons, the particles that carry light, are so polite. Seriously, because the math is abelian, they don't interact with each other. Two flashlight beams can pass right through one another, and they don't care. They just keep going. Their actions commute.
But inside an atom, it is a whole different ballgame. The strong and weak nuclear forces, the stuff that holds our matter together and drives radioactive decay, they are described by those complex non-abelian groups, SU2 and SU3. In here, order is king. And the consequence here is, well, it's wild. Unlike those polite photons, the particles that carry the strong force, called gluons, are not polite at all. Because their math is non-abelian, they interact directly with each other. They're sticky. And this self-interaction creates the insanely powerful force that glues quarks together inside protons and neutrons, a phenomenon called confinement. It's why nuclei exist at all. So we have this simple, orderly abelian force and these complex, intertwined non-abelian forces. Physicists have put all this together into one of the most successful theories ever, the standard model of particle physics. And its heart and soul can be written in one beautiful line of code. This is it. This is the symmetry group of the standard model. It looks almost comically simple, but this short mathematical sentence describes every fundamental particle and every force we know, except for gravity. It's like a poem written in the language of group theory. So let's crack this code open. SU3, that's the complex non-abelian group for the strong force and its sticky gluons. SU2, that's the non-abelian group for the weak force. And that U1 at the end, that's our simple abelian group for electromagnetism and its polite photons. Everything we just talked about, it's all right there. So when you boil it all down, the fundamental nature of our universe, from how a light bulb works to why the sun shines, is dictated by whether its underlying symmetries are simple and orderly or complex and intertwined. Our universe is literally written in this mathematical code, and it just leaves you with this incredible question. What new, maybe even more complex symmetries will we have to find to finally read the rest of the story?